Thank you. Can you hear me all right?
Yeah.
Perfect. Okay. Let's start with a quick show of hands. How many people have done Rust in any way before? Oh, that's a good balance mix. So great. So hopefully we'll have some fun today. Okay, let me start with a very quick introduction. Before I do that, you can scan the QR code or go to the link you see there if you want to have the slides. They're already available online. I'll be showing some code examples, so may be useful if you want to review these things later. So my name is Luciano. I am an AWS serverless hero. I work for a company called Fortiorem as a senior architect. And if you have been in the Node.js space, you might have heard my name because of my contribution to this book. Totally not relevant to this talk, but if it's something that you have read, I'd be really curious to get your opinion afterwards. I'm very available online, all sorts of social network and stuff. You can find me and chat with me. So if you want to connect, you can find all my links in this link tree. A little bit about Fortiorem. We are an AWS partner, so we do consulting business around AWS. We help our customers with cloud migrations, training, cloud enablement, cutting costs. We have been doing lots of interesting work in the financial industry, specifically building high-performance serverless applications. We even have a blog post published with AWS with some of our work. So if all of this stuff sounds interesting, also happy to chat about all of this. But one thing that I'm particularly proud is that at Fortiorem we spend a significant amount of our time creating content. And one of the things that we do is we have this weekly podcast called AWS Bytes, where we share all the things that we learn about AWS. So we have been going on for about 2 years. We have more than 100 episodes. So I think we covered a lot of topics. So let me know if you have bumped into some of our videos and if you have any suggestion on what we can improve or what we can cover next. Okay, let's get into the meaty bits. Why do I like Rust? And it's a very opinionated question, so I'm going to try to give you my part to this answer. The first thing is that it's a very performance and memory safe language, but this is not really the most exciting thing. What I really like is the strongly type system that the language has, which is not necessarily something new. There are some novel things, but you can see that the designers of the language are taking lots of inspirations from languages like Haskell, C++, OCaml, even JavaScript and Ruby. So if you see the syntax and if you have done any of these other languages, you will definitely spot some things that will feel familiar to you. There is a great built-in package manager called Cargo. So if you need to install dependencies, bootstrap a new project, compile, even cross-compile, Cargo will help you to do all of that in an easy way. And it's great to have this tool already built in the standard tool chain. And because of that, there is already a great ecosystem of libraries. Like, I have been using Rust for the last couple of years, a bit more intensely, and I never had the case where I needed a library and I couldn't find it. Actually, more often than not, you have too many libraries and you need to figure out which one is the right one. And finally, there are other things in the language that are really useful, and I'm going to try to give you a super quick demo, like pattern matching, no-null types, and the option and the result types. Now, let me show you a quick example just to show you why I really like these particular features of the language. Let's say that we want to read an environment variable. For instance, we want to read the AWS region. This is something very common in all sorts of programs. And if you have done this before, you have probably been burned by the possible case where you were expecting that the environment variable was set, but then in your actual process, that environment variable was not set. So in other languages, it's on you to check if the variable is set. What do you do? In Rust, things are a little bit different because you don't get a string value assigned to region, but you get a slightly different object type, which is called a result. And the result tries to represent the two possible outcomes. You can have the happy path, so when the value is set and you get a string, or you can have the sad path when the variable is not set and you get an error. And the idea is that you cannot just read the value and ignore the error case, because this object will force you to decide how do you want to handle the potential absence of this value. And there are at least 3 different ways you can do that, depending what you are trying to achieve. One way is where you can be very explicit. You can use the pattern matching to say, This is how I'm going to handle the happy path. This is how I'm going to handle the sad path. So you can explicitly say, these are the two branches that can happen in my program. Another case is when you cannot continue if the value is not there, then you can use this shortcut where you can say expect. And what expect does is basically saying, if the value is not there, there is nothing else we can do in this program, so just panic, let the program crash, and give a very descriptive error message to the user so that they can fix the program, they can fix the execution of that program by making sure that the environment variable is set, and try again. And in that case, we just get a string straight away because we are effectively telling Rust, okay, I need the string to go ahead. If the string is not there, just crash. And another option is when, if the value is not there, maybe we can provide a useful default. For instance, this is a region. It can be any AWS region. But if the region is not set by the user, we can default to EU West 1, for example. In this case, we can use this piece of syntax called unwrap or else, which basically allows us to say, try to get the value from this result type. But if the value is not there, use the default that is provided by this closure function. I'm showing you all of this just to make the case that Rust as a language is designed to let you, as a developer, be very thoughtful about all the possible edge cases and errors that can happen in your program. So because of that, I have a feeling that generally when you write programs in Rust, they tend to be a little bit more robust because the language is kind of forcing you to go through this exercise of thinking, well, I cannot just use this value without ignoring a possible error or the absence of that particular value. Okay, we are talking about Rust in the context of serverless. So how do we define serverless? Probably everyone here is familiar with that, so I'm going to go very quickly. For me, serverless is a way to run applications in the cloud. Of course, there are servers. We know that at this point. But the good thing is that we don't need to manage those servers. We don't really need to think about when do they get updated, what kind of operative system, and lots of details like that. We write our code in small units of compute. Generally, we call them functions, and these functions are triggered by events. So we need to think about our applications as number of events that can trigger different functions, and our business logic is written inside those functions. And the best thing, and this is why Rust is even more relevant here, is that we only pay for what we use. So let's review a little bit what is the pricing model when it comes to Lambda. We can summarize it with this formula, where the cost is equal to allocated memory multiplied by time. And when I say allocated memory, that is a unit of price that depends on how much memory do you assign to your Lambda. It's not the memory that actually is used by your Lambda invocation, but it's the memory that you pre-allocated as the maximum memory that the Lambda can use. For instance, if you go for 128 megabytes, depending on the region that you deploy your Lambda into, there will be a unit of price associated to that. Then you need to see how many milliseconds are you running your Lambda, and then multiply the unit of price for the number of milliseconds. And this is how you get your execution price for a Lambda function. Now, if we take Lambda and Rust together, one of the benefits of this combination is that you have a very, very cost-effective solution, because Rust as a language is designed to be very memory efficient. So that means that you can keep the memory part of that equation very low. So the unit, in my experience, I generally just go with 128 megabytes as a default, and generally is more than sufficient. Only when I'm doing something very memory intensive, I decide to bump it up. And the other thing is that because Lambda can give you very fast execution times as well, allows you to reduce also the other dimension of cost, so the time that you spend executing your code. So this is why Lambda can be very, very cost effective, especially when compared to other runtimes. Also, if cold start is a problem, maybe you are building web APIs and you have a user waiting on the line for every request. So when you have a cold start, it can be a little bit annoying for your users to having to wait a little bit longer. You can use Rust to reduce cold starts, and actually quite significantly, there is a benchmark by Maxime David, and in this benchmark you can see that Rust and C++ are competing between which one is the fastest one a cold starts. Depending on the architecture, depending on the memory, one or the other might be the winner, but only very slightly. And if you ever need to do multi-thread stuff in Lambda, to be fair, it's something very rare. I personally haven't had many use cases of that, but if you ever need to do that, you can use Rust to have a little bit of extra peace of mind that you are doing things correctly. You're not going to have data races or other kinds of memory issues. And we have already seen some examples on why null types and error primitives can be very good for you to think a little bit more of the edge cases and make sure you have fewer bugs in your code. Now, maybe I've convinced you. Maybe you want to try and create your first Lambda in Rust. So what do? You go into the web console, you go into Lambda, and you create a new Lambda, and then you go and select your own runtime. And you start to see Node.js, Python, Java, .NET, Go, Ruby, the usual suspects, and custom. And you are maybe wondering, okay, where is Rust? Like, what are we talking about, right? And actually, you might have noticed, if you have used Go before, that even Go has disappeared from there. So there is something weird happening there. And my reading of it is that AWS has decided that all the compiled languages, they're probably a little bit better suited for be a custom runtime. And hopefully the reason why that is the case is going to be apparent as we go through the rest of the presentation. So the idea is that you cannot just use a managed Rust runtime, but you have to use a custom runtime. And of course, that doesn't mean that you need to build your own custom runtime. There is one provided by AWS as a library. But you're maybe wondering, what the hell is a custom runtime, right? And to really understand what a custom runtime is, we need to look a little bit more into the Lambda execution model. So we say that Lambda is a serverless service. So it should run only when needed. There is an event, we need to do something, then our Lambda exists. If there is nothing happening, our Lambda doesn't need to exist. So the code is generally stored in S3, and when the event happens, AWS needs to do some magic behind the scenes to make sure to bring up the necessary infrastructure, load our code from S3, and then start to execute our code. And all of that stuff happens for the first time. For instance, if there is an event, nothing is there provisioned, AWS will need to do all of that. This is generally called a cold start, and it might take a little bit longer to do all of that for you. But if there is an instance available, of course, AWS is smart enough to reuse that instance. And in that case, you don't really have a cold start. Your code is executed straight away, and this is generally called a warm start. And of course, because we are not paying for idle, AWS eventually is going to reclaim resources if our Lambda is not running for a while. So all of these things are managed by AWS, but that means that when our Lambda is up there running, there needs to be some piece of logic that interacts with the AWS control plane. And this is generally called the runtime. So we are used to think with managed runtimes only about our handler. This is the part that we focus the most about. But there is this runtime piece that is hidden in the managed runtimes. But if we use our custom runtimes, this is something that we need to think a little bit more and understand how it works. So imagine that you are a Lambda. You are just spawned up. What do, right? You don't know what is the event even, right? So the first thing that the runtime does is it's going to use an API to talk with the control plane in AWS to ask for events. Is there an event that I can handle? And most likely there is going to be an event, because if that Lambda exists, probably it's because it was created after an event arrived in the system. So the event is propagated as a JSON message to the runtime. At this point, the runtime doesn't have any business logic. So it's going to delegate doing something useful to the handler. This is the code that we write with our business logic. So this is where interesting stuff is happening. Eventually, there will be a response or an error, which is sent back to the runtime so that the runtime can propagate it back to AWS. Why does it need to be propagated back? Because imagine this is an HTTP request. There is a client making a request, gets converted to an event. The event arrives into our handler, produces a response. We need to return that response all the way back to the client. So this is why the runtime is there to make sure that all this information comes in and out in the right way. And if you use that library that I was mentioning before, that AWS Lambda Rust runtime built by the AWS team, it's already implementing in Rust all this logic for doing the polling, for returning errors, so you don't need to implement all of that stuff. You just need to use the library. So where do we start? There is actually a very useful tool called Cargo Lambda that you can install, and it's also built by the open source part of AWS. And Cargo Lambda is a tool, a CLI tool that you can use, for instance, to bootstrap a new Lambda. So you want to start a new Lambda project, you don't know where to start, you just say Cargo Lambda init. It's going to ask you a few questions. For instance, is it an HTTP function, or maybe is it another event? Here we are selecting S3, for example. And when we select S3, we are going to end up with a code that looks like this. And don't worry too much about the code, I just want to show you that there are two parts. The first part is that we are using that runtime library. We are importing some types and functions from it. And then we have this main part. This is effectively our init phase. So this is going to happen only when our Lambda is started for the first time. And we can set up, for instance, logging. We could create DynamoDB clients. We can do all the usual initialization stuff that you have seen with JavaScript and Python. And then at some point, we call this run function from the Lambda runtime library. What this run function does is effectively a loop. This is going to do an endless loop, and it's going to keep polling for events for you. And when there is a new event available, it's going to call this function handler, which is also created by the boilerplate creator, but this is where we are going to put our business logic. So in reality, most of the time, we don't need to worry too much about the runtime and the handler. We're just going to run Cargo Lambda init and then write the code in our function handler. Here, this is an S3 event, so we are just logging, for instance, the objects that were created in an S3 bucket. Okay, the other cool thing I want to show you is that Cargo Lambda comes with a nice built-in simulator that you can use to test your code locally. So we are not shipping our Lambda to AWS just yet. We can use Cargo Lambda watch to start the local simulator in a terminal. And in the other terminal, we can say Cargo Lambda invoke with an event. And this is going to run everything locally so that we can test our Lambda before we deploy. But we say that Rust is a very good typed language. So can we take advantage of the type system for typing our requests and responses so that we can make sure that we use them correctly? We access the right fields, we return the response with the right fields and the right values. And if you have done any Lambda, you know that sometimes, for instance, when you use JavaScript, it's always a bit tricky to understand, okay, this is an API gateway event. What is the field that tells me, I don't know, the method? Or how do I parse a query string? And every single time you have to check the documentation and make sure you do everything correctly. So here, because we have a type system, we can have a little bit of a more guided experience. So in our first example, we were using an S3 event. So an object is created in S3. We get an event into our Lambda. That event needs to describe the object that was created on S3. And we can use this particular type as the input of our function handler. So Lambda event and then S3 event. And for the response, because we don't really need to do anything, this is an asynchronous invocation, we have this open and close parentheses. This is what's called a unit type. And it basically is a value that doesn't contain any actual meaningful value. So in this particular case, we get an S3 event, we produce nothing back. But what if we want to use another kind of event? And there are a few different cases. One case is, okay, if we need an event from another AWS service, there is actually a library that we can use that is called AWS Lambda Events, which is the one that was already provisioned for us when we used Cargo Lambda init and selected S3. It was behind the scenes already installing this library and configuring it correctly so that we can use the S3 event type. But there are so many other events. I think almost every possible event is supported. And if it's not, you can easily contribute to the open source repository. The maintainers are actually very, very quick to do all sorts of changes if they see that there is a good use case for a new event type. And I'm going to show you just a very quick example to show you why this can be very useful. Let's say that we want to create a Lambda function that can process jobs from an SQS queue. So the idea is that you have jobs coming in the queue, then you can have multiple Lambdas taking all these jobs and executing them. And you might know that there is an event source mapper there that is basically polling the queue for you and creating the events for the Lambdas. So we need to write a Lambda in Rust that has the SQS type, and not just the input type, but also the response type. And we can actually configure this AWS Lambda events crate or library to use specifically the feature SQS. This is a little bit of an optimization trick. In Rust, compilation times can be a little bit longer. So if you use something like this, you're basically saying from this particular library, only compile the SQS types because I don't need anything else. So if you use the cargo lambda init command, it's going to do all of that behind the scenes for you. But then if you need to change your lambda code later on, just be aware that you might need to enable other features that weren't enabled at the beginning. Okay, at this point, we can write some code that looks like this. So we can import all the types from the library that we just mentioned. Our input is going to be a Lambda event of type SQS event. So that type will contain all the fields that allows us to access all the different records in the event. Then for every record, we can access all the different attributes. Everything is typed, so it's very easy to understand what are the right fields that we need to use. But the more interesting piece is this SQS batch response. Now, if you have ever done job processing from SQS, you know that you don't get one job at a time. You get a batch that might contain multiple jobs. And there is always a very common annoying problem, which is, okay, what if I have to process 10 jobs? 9 of them were okay and 1 failed. What do I do next? Do I need to retry the entire batch? Or maybe do I need to manage my own entire retry logic? It can get very complicated very quickly, but there is actually this feature that is built in the Lambda integration where you can return as a response the IDs of the jobs that failed. If you create a payload that complies to this standard, basically AWS will know, okay, all the jobs succeeded except the ones that you mentioned here in your response. So AWS can reschedule those failed jobs directly for you. So here what we are doing is effectively using this response type to be sure that we are constructing the correct response so that if any job failed, AWS can reschedule that correctly. Now, this was an example when you are creating AWS-specific integrations. For instance, in that case was S3, then we saw SQS or any other of the types that are supported. But what if you want to do something custom? Maybe you are working on a step function. I have an example here for an automation I built for a newsletter where I have a bunch of custom steps, and those steps are built with serverless function using Lambda and Rust. So what do we do there? Because if you ever done a step function, you know that you can accept any kind of input that makes sense for you, and you can produce any kind of output that makes sense for you in that particular step. So how do we specify custom inputs and outputs? There are 2 very useful libraries in the Rust ecosystem. One is called Serdi, which is a generic serialization, deserialization library, a little bit like Jackson in Java if you want. And then there is Serdi.json, which is the specific implementation of Serdi that supports the JSON language. You can use these 2 crates to basically create your own types. For instance, here I created a request type and a response type, and then I can just use this request and response as input and output of my function handler. And by just adding these annotations, derive, Serdi deserialize, and Serdi serialize, I'm basically saying this type can be deserialized from JSON, this other type can be serialized from JSON, and the Lambda runtime in Rust is going to make sure to do all the necessary conversion from and to JSON when needed. So we don't even have to think about JSON directly. We don't have to call JSON serialize, for instance. The runtime is going to do all of that if we just use this particular library. Okay, I have here another example that shows how we can test all of this locally, and you can see that, for instance, if you want to send a custom event, you can also do that with the local simulator. Now, I'm going to speed up just to make sure we cover everything we want to cover today. The other use case is that what if you want to write a Lambda that accepts any arbitrary JSON? Like sometimes can be just a string, sometimes could be an array, sometimes can be an object with nested stuff. How do you do that? If this is a strongly typed language, how can you support the case where the object can be anything, really? And there is an option for that as well. So that serdJSON library I mentioned before has a type called serdJSON value, which can represent any valid JSON value. So it can be a null, it can be a string, it can be an array, an object, and so on. The only annoying thing, if you really have to do this, is because Rust, as we said, is a little bit strict and it wants to make sure that you cover all the possible edge cases, is that the code can get ugly very, very quickly. So you can see here that we need to do event.payload is going to give us access to the actual event structure. Then we need to say as object, which means try to read it as an object, but it might not be an object. So what do you do if it's not an object? Then here we are just saying unwrap, which is like expect. So it's going to panic if it's not an object. Then you need to say, OK, now I want to read the field URL, but that field might not be there. So what do we do if it's not there? And you need to unwrap again or do more complicated error handling. And it can go on and on, like just reading a nested field can get very complicated. But on the other end, you are very sure that you are thinking about all the possible edge cases. OK, so the last thing I want to show you is that if you want to do HTTP-based functions, there is actually a very nice shortcut. So remember that when we did cargo lambda init, the first question was, is this an HTTP function? If you say yes, you end up with some code that looks like this, where this time, rather than having that lambda event type, we actually have a request and response type. And these are objects that mimic the HTTP specification a little bit closer. So they are a little bit nicer to work with. But behind the scenes, it's still JSON that gets serialized and deserialized for you. It's still using the Lambda proxy integration. So it's still a very native Lambda experience. It's not trying to wrap an entire HTTP framework inside a Lambda. OK, at this point, you know how to write all kinds of Lambdas in Rust. How do we deploy? There is a command that you can run there. And it's going to do a bunch of magic for you, including, for instance, if you use ARM as a target, it can cross-compile from any operative system and any CPU directly to ARM, which is really nice because it means you don't have to be worried about recreating a CI/CD environment that mimics exactly your target. Now, when you deploy with Cargo Lambda, it's pretty cool, but then you end up with something like this, which shows two problems. The first problem is like, what the hell is all of that? And this is obvious because this is a binary compiled language. So you don't get the freedom that you get with Python or JavaScript, where you can go in the console, change the code, save, try again, every time you need to build and deploy. Because it's a binary, so it's not very easy to modify by hand. Maybe you can do that, but I don't know. I wouldn't try. The other problem is that there is no trigger configured. And this is because while we use Cargo Lambda for packaging and deploying, when we say Cargo Lambda deploy, it's just one command. Like it doesn't know about our entire application, our entire infrastructure, what is the event, what is the stack that we want to deploy into. So it's literally just going to package a zip and create a new Lambda for you. So it's not the most ideal way to build serious applications. But thankfully, you can use Cargo Lambda with SAM or even CDK if you want. And the idea is that at that point, you get the best of both worlds. You get to define all your infrastructure as code with SAM, so you can define all of your dependency. You can have one stack that describes your application. But then when you have Lambdas written in Rust as part of your stack, you can tell Cargo Lambda to do all the building and packaging correctly. And you can even test an API gateway locally with SAM and run Rust code behind the scenes. It looks a little bit like this. So you have to provide this extra little bit of metadata where you have to say build method Rust Cargo Lambda. And then the other thing is, because this is a custom runtime, you need to say that the handler is Bootstrap and specify that runtime is provided AL 2023. And then you can configure your events as usual. Because this feature is still beta, as far as I know, you need to enable this little flag in the configuration. Otherwise, every time you call sum, you need to pass --. I think it's called enable beta features or something like that. Okay, and when you sum, then you get some build, some local start API, and some deploy. And behind the scenes, every time it needs to do something with Lambda Rust, it's going to use Cargo Lambda for you. Now, I'm just going to give you some closing notes. I think Lambda is great, but I think everyone knew that, and we all agree on that. But writing Lambdas in Rust is fun and can be very cost efficient. It's not very common still. I think it's still a relatively new trend in our community, so it's something that I encourage you to experiment with a little bit more, play with it, have fun, and if you learn something new, write an article, make a video, share it with your colleagues, do an internal presentation. I think the more we learn, the more we share, the more we will be able to have use cases and understand if this is really convenient as it looks, or maybe there are things that we need to improve in the community. I have a few more examples that you can see here. For instance, this is an application that can track and notify you about earthquakes. Here I have an open source REST API gateway authorizer for OIDC tokens. So if you do private REST API gateways and you need to validate OIDC tokens, this can be a useful solution. I also created some benchmarks comparing it with a Python implementation. So if you're curious, you can check all of that as well. And then if you want more, I have an announcement. James and I are working on a book called Crafting Lambda Function in Rust. It is still very early. There is still very little written. We are starting to give it away with a very generous discount. So if that's something interesting for you, you can get the initial chapters and then the new ones as they come. And if you like the mascot, I have stickers. So come find me afterwards for that. Thank you very much. I don't know if we have times for questions, but if don't, cool. Maybe one question then. Go ahead.
What about the ecosystem? For example, if you write Lambdas in, let's say, TypeScript or Python, there's the power tools and these kind of things. And what about X-ray and observability?
That's a very good question. So it is still maybe a little bit early, so you don't have all the many libraries that you have for Python and TypeScript and so on. There are some interesting things though. For instance, if you get the power tool, one of the cool things that they do is basically using the middleware pattern to allow you to keep your core small and then build around it. And this is how power tool works, by giving you a bunch of middlewares to extend your Lambda function. So there is a middleware engine that is built in the Rust runtime. So by default, you get that. You just need to hook into it. It's not really well known at this point. It's kind of one of those hidden features, and there aren't many examples on how to use it. So I have a feeling that the more people will start to explore this field, the more people will start to realize, oh, there is a middleware engine there. Why don't we write a few middlewares just to make it easier to do logging and so on? Other than that, there are already some very good libraries for logging, doing logging in JSON, structured logging, that come from the wider Rust ecosystem, and you get them by default when you use the bootstrap mechanism of Cargo Lambda. So it's not that bad, but I think it could be better, so it's just probably a matter of time. Thank you, everyone.